When a star collapses, its quantum information appears to vanish. To solve this paradox, physicists spent years developing three specific proposals: islands, fuzzballs, and firewalls. These three ideas have generated thousands of research papers and decades of intense debate. If you follow the literature, it looks like a three-way fight to determine which concept provides the singular, correct description of reality. But a closer look at the math reveals a mismatch. The island formula is a method for calculating a specific curve. Fuzzballs are a proposal for physical microstates. These aren't different answers to the same question. They are answers to different questions entirely. Because the participants haven't defined the specific role of their proposals, they spend years debating a conflict that may not actually exist. This lack of a shared vocabulary keeps the discourse in a state of perpetual structural confusion. In this environment, it's easy to overlook foundational gaps. A theorist can adjust free parameters until their equations happen to fit observed data, claiming a deep mathematical derivation when they have actually only performed a complex act of parameter fitting. To create clarity, we need the workbench. This isn't a new physical theory. It is a methodological inventory. It is a structured protocol for forcing every theoretical claim into the open so it can be independently examined. Progress in high-energy physics now depends on this kind of disciplined visibility. We need a system that identifies exactly what a theory has proven, what it has assumed, and where the math is currently silent. The first stage of a workbench audit is the function class assignment. Before we look at the equations, we must define what the framework is actually trying to do. In the black hole debate, the firewall proposal routes into diagnostic argument, a tool exposing contradictions. Fuzzballs drop into candidate ontology, a proposal for black hole composition. The island formula enters reconstruction mechanism, a specific calculation tool. Sorting these proposals into functional lanes changes the nature of the dispute. When we see one is a diagnostic tool and the other a microphysical model, the requirement for them to compete disappears. Once categorized, the workbench applies the explanation ladder. This four-tier system distinguishes between a result following automatically from a theory's math and a result simply inserted as an assumption. Rule A, the inverse check, tests if real-world data can work backwards to limit foundational ingredients. Without this path, the connection snaps. Rule D, the parameter space warning, identifies math expanding just to fit data, labeling it accommodation rather than true explanation. These diagnostic rules act as a filter. They separate the durable physical content of a paper from the stylistic or rhetorical choices used to present it. Cataloging every claim in a 50-page physics paper requires massive semantic processing. This is where we employ a large language model as a reasoning assistant. The AI functions as an adversarial clerk. Its job is to ingest the literature and extract the substrate variables, map out the internal dynamics, and pinpoint the mathematical invariants, while following a strict protocol forbidding claims of absolute truth. By limiting the AI to this clerical extraction, we ensure the machine handles the labor of organization, while the final scientific adjudication remains entirely with human experts. The audit concludes with a mandatory incompleteness declaration. The authors must explicitly state which of their core claims remain unproven and which questions are currently undecidable within their own math. This is a Gödel-Humboldt approach. The mathematician Kurt Gödel demonstrated that no complex system can certify its own completeness. The workbench turns this mathematical reality into a standard for scientific honesty. In this system, a framework that admits its gaps and provides a map of its own missing proofs is valued more highly than one that obscures its limitations. The final output is a legible scorecard. It provides a formal audit trail of what a theory has earned the right to claim, what it has merely assumed, and exactly where the next generation of researchers needs to focus. The workbench is not designed to solve the laws of nature through automation. It is designed to enforce epistemic transparency. By using strict protocols to organize our best ideas, we ensure that as we reach for the ultimate laws of physics, we are building on a foundation of verified, accountable ground.